everyone, just back with another lecture video on chapter 14. This is going to be on alternative energy resources. And again, I say this every time, and I apologize. I'm going to try to make this video a little shorter this time. I know we're getting close to the end of the semester. However, we're starting to get into some of the topics that most of you probably thought we were going to be talking about more during the semester, and that is the human influence and effect on our planet, and what we're doing and what we can do currently to the planet and what we can do to help the planet going forward and help ourselves as well. So as we start off this conversation, one thing I want to mention, and I put this visual up, and I put this up for a reason, because we're going to talk about philosophy a little bit before we get into these renewable energy resources. So in today's world, it's much different than when I was young. I kind of feel for y'all really, because you've got so much stuff to wade through, so many sources of information, so many ways to find things. You would think that would be a good thing, and that's what we always thought. One thing that people said back when I was young was, we lack the connectivity and the communication skills. If everybody had the internet, we're going to have access to all this information, and it's going to make the world a smarter place. Well, not really, because what you have is you've had people that take advantage of that. And when people have an ulterior motive, when they have an agenda to push, it's very easy for them to put out incorrect information, either accidentally or on purpose. And we see that in today's world a lot, from the fake news sources that we have out there to the conspiracy theorists to some politicians. We even have a major political party now that attacks education. I don't understand why, but they do. So the reason I put this visual up is to show you that there are different perspectives on a lot of different topics, and climate change and renewable energy is one of those. Depending on where you look, everything we're going to talk about today, somebody has shot these ideas down for some reason. They're too hard, they're too expensive, it's not practical, it won't solve the problem. And this visual, I think, is an excellent one, because it shows you that while there is the truth here in the middle, which is a cylinder, depending on what angle you look at it, or in this case you're shining light on it, if you shine a light this way, the shadow looks like a square. If you shine it this way, it looks like a circle. But the truth is much more complicated than that. There's a lot more that goes into a cylinder, because it's 3D. You can think about it physically, but this is kind of a paradigm for what we're talking about. What's really happening in the world is more complicated than what some people would like for you to believe. And I'm touching on this right now because I know that some of you may have pre-existing ideas about some of these things just based on stuff that you've heard. So the intelligent person will gather the information, they will research it, and they would look at all sides of the argument. Is this good? Is it not good? Is it practical? Is it too expensive? There's a million different types of arguments that can be made on these very simple topics. And I say they're very simple because common sense kind of leads you down a path to how these things should go, but common sense has left the building, it seems like, in this world today. So I just wanted to put this out here because you might see or hear different things on these topics, and you might think, wait a minute, that's not what I knew about this before, or that's not what so-and-so, my favorite politician, said about this issue. Or here in Kentucky, we hear all the time about how great coal is, and it provides jobs and all that, which part of that is true when you look at it from a certain angle, but there's always that cost-benefit relationship. What's it costing? What's the benefit? What are our options going forward? And that's the only reason I wanted to put this out there for those of you that might have these other ideas, or you might hear different things about these, because for everything we talk about, somebody's going to say, no, it's not going to work. No, that's ridiculous. That's impossible. So I just wanted to put that out there. So this chapter we're going to talk about alternative energy resources. So in today's world, that pretty much usually always means renewable resources. Now, the way that this author with this textbook has set this up, there's a little background here. Like when back in the old days, I say we as a species, back in the industrial countries, back in the day in England, this is showing somebody in the, I think, 1890s or a little bit before that, they actually used a lot of coal gas. They would take coal and they would convert it to a gas they could burn, and they used that as a fuel. As you can imagine, you probably didn't want to be breathing this stuff very much back then. You can even look down this street right here and see how foggy it looks and all that. So that probably wasn't a great time to be alive back in London back in those days. But this author also puts in here non-conventional fossil fuel resources. So I'm going to just go through these really quickly. And it is non-conventional, and the title of this chapter is Alternative Energy Resources. But I would have actually put this in with our conventional fossil fuel resources, because even though we don't use these fossil fuel resources a lot, and I can see why he would put it into the alternative category, they're still fossil fuels. They're still going to present the same problems that we had with fossil fuels with regards to extraction, pollution, and all that. They're just going to be more expensive and harder to extract than the conventional. You have to think of it as we've already hit all the easy stuff. Now we're moving on to the harder stuff to get. So this stuff is not very attractive with regards to going forward on an environmental topic. Now, if you're in the camp that we just should use every fossil fuel that we have on this planet before we even think about anything else, then yeah, you're going to want to go and drill more and mine more and try to get this stuff out of the ground. So the big problem with that, though, is a few things. One is, environmentally, it's just as dirty, if not more dirty, than conventional fossil fuels. Two is, it's harder to get at, or we would have already gotten it. So it's harder to get, it's harder to transport, and it costs a lot more to process into the usable stuff that we need it for, like gasoline. So people that are whining about gasoline prices today, if we had to refine this stuff, it's going to be unbearable how expensive it's going to be. So that's my general opinion about these. I'm not going to go into great detail on each one of these, but that's the 50,000 foot view on these. They are hydrocarbons. They are similar to oil and gas, and even some instances coal, and it's going to not only pollute the environment as much by burning these, but it's going to pollute more even getting to them and then processing them on the back end, and it's going to cost a lot more. So these are going to be a lot more expensive to even get. Even if we could do it, it's going to cost us, the consumer, more in the long run, and that's just not going to be feasible. You see how crazy people are about gas prices right now, and I understand why they are, because of our economy. However, this would be worse. So just real quickly, they talk about viscosity of some of these substances. Viscosity, if something is highly viscous, that means it's really thick. So think about tar, how thick tar is. That's high viscosity. Low viscosity is thinner. So what they want is they want to lower the viscosity, which this stuff is very viscous in the ground. So what they do a lot of times is they heat it. They pump steam down or try to heat it in some way so that makes it thinner. Therefore, the pumps can pump it up through the oil wells, or whatever type of well you want to call it, and they can extract it from the ground. So that's one way to do it. So that tells you right there that's going to be expensive. Here's a similar version of that. Some of these are more local. So these are individually, one by one. They send steam down, they heat it, and then they pump it out right away. This one is a bigger operation with an injection well. They're pumping steam down, and they can extract from several wells around the area. This is a map west. This is Utah, Idaho, Wyoming, Colorado. This shows some of these reserves out west. I actually looked into this when I was in my early 20s, beginning my career. I had an acquaintance that was dipping their toe into this. At the time, I looked into it. I was offered a job at it, and I quickly turned it down. Even though I really wanted to move out in this area, it had been really cool to live out there, I was not interested in the least in working in this field. It just did not seem like it was practical, and of course, it wasn't at the time, and it really still isn't. but we're getting to a point where it might be closer to being done more in the near future. Shell Oil did an experiment with this, and again, it was along the same lines. They're injecting steam down here, heating this oil to lower the viscosity so they can pump it. In their case, though, they realized that all this injected steam, i.e. hot water, that went down had to go somewhere. And they realized that it was picking up a lot of pollution, so they actually, around it, drilled a bunch of wells and froze those. So they set up basically an ice wall around these so the water couldn't escape. It probably wasn't very successful. I haven't heard a lot of results on that. But you could imagine, as soon as they're done with this operation, do you think they're going to spend the time and money and effort to keep these frozen forever, to keep that water contained in this area? Or are they just going to leave it and that water's going to get out eventually anyway? I've already told you about what I think about human concern about the environment and the reliability of companies like this, and that's just going to be a problem down the road that really is not needed. Gas hydrates. Now this is a problem right now that's happening in real time with climate change. I've mentioned or alluded to it in previous lessons. So we have our permafrost, our glacial areas in the far northern and southern latitudes, mostly northern because most of the south is ice. But if Antarctica starts thawing out anytime soon in a large scale, probably we'll have some of this down there as well. So there's a lot of organic matter in the soil in these areas, the land areas up north, and under some water bodies as well. And this stuff has been frozen for thousands of years. It's thawing for the very first time now, since thousands and thousands of years ago. This is the warmest this planet has been in thousands of years. So all that organic matter, it's kind of bottling up a lot of methane gas and other greenhouse gases, but methane's the primary one. I'll just talk about that here in this example. And as that permafrost is melting, this gas is escaping. So not only are we contributing to climate change in the warming environment, but this gas that is naturally occurring is being allowed to escape into the atmosphere. And remember, from almost every lecture we've done, that balance is starting to tip. And this is going to be an exponential one. The warmer it gets, the more and more these gases are going to escape the permafrost, and we're going to have more and more problems. Sometimes these gases are underwater bodies, shallow seas, or even lakes. And the changes in pressure, this can be from frozen from temperature or some pressure. And if it gets a little warmer, that pressure might release a little bit. So you get it underwater as well. So here I have a couple of photos I've put into these slides. Most of these PowerPoints are from the publisher of the textbook, but I edit these sometimes. So this is a lake in the northern latitudes, as you can tell, and all these bubbles you see in this ice were methane bubbles that have come up and become frozen in this ice. So the next time it gets warm enough up here, these are going to escape directly into the atmosphere. These are some methane bubbles right here, and as you can see, this person has cracked a hole in the ice and just with the lighter set it on fire. So you're looking at water and ice that's burning from methane right there. Same thing in this picture. This guy punched a hole in the ice, this guy had a lighter, and boom, it just popped up. That's how much methane is just sitting under the ground and is now being able to get into our environment. Now, the reason this is in this chapter is, could we ever harness this? Methane is a gas that we can combust and we could use as energy production. So can we capture this? Well, that's a good question. Could we? Hypothetically, yes. Practically, probably not. Because this is so spread out and it's everywhere up there. So as everything starts to thaw, how do you capture it really, since it's geographical, the spatial distribution of this is so widespread? Maybe we could use ice as our advantage as a limiting tool, and maybe anything that's captured under a lake. I don't know. I'm sure somebody's looked at this, but right now it's not a practical thing to do. But this is a potential source of energy if we could find some scaled version of how to capture it. So now we're going to get into renewables. And this is what really I think is what this chapter is about and what we should focus on. So we have a few different types here. So we have biofuels, which is basically taking hydrocarbons that we've already talked about and blending them with some basically ethanol, alcohol from the processing of plants. A lot of corn in this. You hear about corn biofuel. Um, that ethanol is added to gas. It's an additive that it actually burns a little cleaner, so it's not as harmful as far as producing the hydrocarbons into the atmosphere, the greenhouse gases. However, the amount of hydrocarbons that we use to process that corn, the farm equipment, the fertilizer, everything that goes into producing that corn, by the time it gets into the biofuel form, we've really canceled out any benefits, or actually probably spent more in the carbon footprint by producing these. So as a greenhouse gas help, it's not much. Now, one reason that they do add it to fuel so much in the United States is it does help to lower the cost of the gasoline a little bit. And that's why we currently use so much of it. You'll see in a slide a little bit later that we've increased our use of this a lot. Initially, it's for reducing those greenhouse gases, but no, now it's more for a price control than anything else. We have hydroelectric power, we have nuclear power, solar, wind, and tidal, and geothermal. So we're going to briefly go through some of these in this presentation. Carbon-free and renewable, this is the ethanol production, again, primarily from corn, but there are some other plants that they can use if they wanted to use that. And you can see it's really gone up in recent years. And again, back in these early days, it was kind of an experiment to see if it was going to help with the greenhouse gases. Now it's more of a price control. It's cheaper to do this and blend it with gas than to just use straight gas. So hydroelectric. So traditionally, we've thought of hydroelectric as a dam on a river. This was in the textbook. I had never heard of this before. It's a pretty unique conversation piece. This is actually a lake that they built. So think about a dam across a river. They actually built a dam all the way around this. It's an elevated lake. They built it up from the surrounding countryside. Looks like it's in the shape of a heart here or something. I don't know why, but it looks like that is. And they actually pump, there's a river down here close somewhere. They're pumping water up into this lake. They could do it from groundwater too, depending on where they are. And then after they pump it up here, they let it drain back down through a spillway, not a spillway, but a tunnel. A spillway would be more in a lake. And there's generators inside these tunnels, so the flow of water spins these generators, and that generates electricity. So you're using gravity to generate electricity, so that's a good thing. The problem I see with this is, and it might not be a problem, it's going to be a net gain and loss kind of thing. So you're going to have to pump water up into this lake. So how much energy is that going to take? If you're using as much energy to pump water up to the lake as it produces on the back end, then it's a net zero. It's really not helping you a lot. So I would be curious to see the numbers on that to see if that is really something practical. Now, if this was located in the rainforest and this water was somehow able to be naturally replenished in some degree, then maybe, but that would take an excessive amount of rainfall just to fall on top of this with no input from runoff anywhere. So I'm kind of curious to see the numbers on this. Now here are your traditional hydroelectric dams. Now these are good and bad. Again, you're using gravity, the flow of water flows downhill all the time, so any river's flowing downhill. So what they do is they make a dam across a river, you make a reservoir behind it, and as that water passes through the dam, it goes through, I'll use this dam, you can see it a little better, you see these big pipes coming into this structure. So the water that's flowing through this dam, in high rain precipitation events, they'll let it flow through there and just it flows down through the river. The natural riverbed below the dam. But here they're actually generating power. The water's flowing through these pipes. You can see it's coming out in the tailwater down here in this area. There's turbines inside this building, and that gravity flow of water is producing electricity by turning those turbines. And the turning of those turbines produce electricity. So that's how a hydroelectric dam works. Now these are very efficient. They work really, really well. They produce a lot of electricity. The downside of these are they destroy ecosystems. Now I picked this picture right here in particular because this looks like it's kind of in a hilly or mountainous, semi-mountainous area. I've told you before in other videos, I'm a big whitewater kayaker and rafter. This was probably a pretty awesome whitewater river right here, judging by the terrain, before this dam was here. Now it's a lake. It's under several, probably up to 50, 60, maybe 100 feet of water. And that ecosystem, as long as this water's backed up, which might be in a narrow channel like this, might be several miles, that ecosystem has been destroyed, and now you have a lake that's not natural to this type of environment. So that's the drawback to these hydroelectric dams. Now, some of you might not think that's a big deal. I prefer natural flowing water. But also, if you have some species in this river, let's say this is on, I'm not sure exactly where this picture was taken. Let's say this is on the west coast where you have big salmon runs up the rivers out there. This is a natural barrier. No fish are going to be able to swim up past this dam. So you have cut this river off right here, either from the ocean or other freshwater fish swimming upriver to spawn and stuff like that. So you basically just cut off this ecosystem right in half right here. So that's the drawback to dams, is that they can really disturb ecosystems. Nuclear power. This is power I mentioned in our last lesson. This is a very good energy source. It's virtually, it's renewable in the fact that we have plenty of material. We can get radioactive material, the uranium, pretty readily. And once we get it, it lasts for a very long time, because once you start this process, it continues on its own. You don't have to input a lot of energy into a nuclear power plant to get energy out of it. And it will run for years and years and years and years. So that's the plus of this. And I'm not going to get into the chemistry right here. This is in your textbook. You can go over this yourself. But basically, there's two types. There's fusion and fission. And the drawback to nuclear is high reward, but it's a high risk. And what I mentioned in our last lesson was, if something goes wrong with a nuclear plant, it can go really wrong and have really big consequences. So that's the drawback to nuclear. Right now, it's been weaponized in Ukraine. The Russians are threatening to blow up some nuclear reactors over there that they use for power generation. If they were to blow one of these up or destroy one of these, you're going to have an entire area of a country uninhabitable because of the radiation. We've had a nuclear accident in the past, 3 Mile Island in the United States, Chernobyl, which was also in Ukraine back in, I think that was the 80s that happened. We had meltdowns of nuclear reactors and made areas around those nuclear reactors pretty much uninhabitable for a while. So again, you've got the problem of something going wrong, and then you do have some waste material from this. After the material breaks down as much as we can break it down to produce energy, you are going to have some radioactive waste over here. In the long run, it's not a huge amount like we produce from like coal plants and stuff like that. As far as the waste from those, it's not nuclear with those, but we still have to be responsible in how and where we store this stuff when it's spent. So again, that goes back to how reliable is humanity? How responsible are we to trust us to be able to do this and do it the correct way? So that's the plus and minus of that. Again, high reward, it's virtually great for the environment if we do it correctly and if we manage it correctly without any accidents. Here's a diagram of how there's two different types of nuclear reactors. Again, I'm not going to go into the details just for time purposes, but you can look at those in the textbook. Here are the existing nuclear power plants that we have in the United States that run today. You can see closest to us, there's a cluster down here in Tennessee. I drive by these often. Oak Ridge is the most prominent one down in the Appalachian part of Tennessee. And you can see here, this is the total nuclear energy that was produced in the United States, and it's pretty much flatlined or even decreased a little since 1990. And again, that's because of the public's doubt about nuclear energy and hesitance to go all in on it. A country like France, they use a lot of nuclear energy in France. So now we go to solar. This is one of the big hot button topics right now. When we talk about renewables, we hear about solar and wind more often than not when we talk about renewables. So solar is a good thing, and it's used quite a bit now actually, but not enough. When we talk about solar, there's a few factors in this, and you're going to hear these factors from the doubters. Well, when the sun doesn't shine, we can't produce electricity. No, that's true in a sense, but there's ways around that. None of these are going to be foolproof. None of these are going to be 100% effective all the time. But if we use a combination of these things together, then we can manage on renewable energy most of the time. Probably 90% of the time easily if we wanted to go that route. So this is the map of the United States, and it indicates how many days of sunshine it averages per year on this map. So you can see the desert Southwest has the most, and as you go north and east, you get less and less. There's kind of a small area up here in the Pacific Northwest. Alaska will never be able to run on solar alone, but there's a lot of other options up there as well. So this kind of shows you where solar is the most advantageous. You can see here in Kentucky, we're around this area right here. We get plenty of solar to function with solar if we needed to. We're not as ideal as the desert Southwest, but we get enough to make it work here, especially if we used it in conjunction with other things. So when we talk about solar, there's two types of solar heating. We have the photovoltaic cells, which those cells in themselves, those are the most common type that you probably are used to seeing. They actually produce electricity directly from the cell. They use the sun's energy to strip electrons within the cell, and that directly produces electricity that can go straight to the electric grid or to use in your home, or to a battery storage system in your home. So that's direct. The panels up here are thermal panels. Now, thermal panels are just designed to get hot, basically. And they'll transfer that heat down into the home. So in the wintertime, you could use thermal cells to help heat your home, or they're really useful for like hot water heaters. When you get hot water in your home, you can set that up for just a thermal cell, not necessarily a photovoltaic cell, and that would heat the water in your home, for instance. And here's just a diagram of the system. Again, this is the hot water heating system that I just mentioned. Battery technology has come a long way, so now we can actually put batteries in the home, kind of like we have in the electric cars now, that can store that energy so you can have electricity throughout the night or even over a couple of days if you don't have much sunshine. Again, it's not foolproof, I understand that, but we have a huge nuclear reactor in the sky that puts enough energy on this planet every day to run power for human needs for years in each day. I want to go back to this as well because you can see how much sun shines down in this area. So another option would be to set up an electrical grid, even in areas far away that don't get the sunshine. If you had a sufficient electrical grid hooked up to solar farms in this area, a relatively small area, now I say a relatively small, I'm talking about with regards to the area of the desert Southwest. So you could have several really large solar farms, small in scale to the size, say, of a state, big to us personally if we go out and look at it, but they could provide the power for the entire United States from this area. We just have to have a way to transport that. So that's another angle you can look at on solar with regards to where it gets the most sunlight. If we can transport that electricity and have that grid set up, then we could be self-sufficient just from one area. This is a concentrated solar plant. Now, the things I just told you were kind of based on a home or the photovoltaic cells. They produce electricity directly. So you might have a huge farm of photovoltaic cells that produce electricity, and you see those in Kentucky sometimes. This one looks a little different than probably what you've seen. These are actually mirrors, and they are focusing the sun's heat, the light and heat, to a central spot here. That's why it's so bright in the center, and it's getting really, really hot. And there's actually a storage system of molten salts that it superheats, and that heat again, goes back to the kinetic energy. Think about turbines. It heats up water that spins turbines and produces electricity like that. So these are not photovoltaic cells here. They're not directly producing the electricity. They're just superheating an area to where that area stays so hot, and they could run for several days without any sun, because that excuse me, those molten salts get so hot they can stay hot for several days producing electricity even if no sun hits this. So this is an example of another type of solar energy that we could use. It's very concentrated, but then we could disperse this energy around the countryside. Wind power is the next one we're talking about. And wind power is, again, something that all the naysayers on the conspiracy theory channels will tell you, oh, it's never going to work. The wind doesn't blow all the time, blah, blah, blah. That's true. We have maps. We have science. You can see where the wind does blow a lot. So that's where you're going to concentrate your wind farms. See, on the coasts, up in the mountains, typically, and on the backside. This is the Great Plains. Very flat on the backside of the Rocky Mountains. So you have a lot of wind out there. So again, you have these large turbines, and these actually produce electricity by spinning. Each one has a generator in it that spins with the wind. It produces that electricity, and then that's put into the grid. And again, the technology is there. If you use this in conjunction with solar, you see that there are several areas that didn't have a lot of sun but have a lot of wind. So we use these two things together, and we could supply a lot of the country with dependable electricity. Even though the wind doesn't blow here in Kentucky all the time, you could still have some wind farms, and when it does blow, you can have it. When it doesn't, you have solar. Again, it's a compromise. You see in Alaska, there's a lot of wind out on the coast. So that's another source that they could use there in addition to something like, say, geothermal. So as you can see, we're kind of building a model here. It's not all just one answer for one specific type. And that goes back to that diagram I showed you in the beginning. It's easy for people to sit back and just throw dirt on something and say, well, that's not going to work because of this. Well, that's not going to work because of that. When I look at that and I think about those people, first of all, they don't understand the big picture, or they have an ulterior motive, such as they might be working for one of these big energy companies and they don't want to lose their source of income, of course. That's very common in our society. Or they just don't get the big picture. And what I mean by that is let's say that your brain was wiped clean and you didn't know anything about energy at all. And I told you, well, we can get energy, but what we're going to have to do is we're going to have to drill down about 2 miles under the Earth's crust. We're going to have to pump this stuff out. We're going to have to build big platforms out in the ocean to do this. And then once we get it up, it's really dirty. We're going to have to ship it to a city where there's a factory, and then we're going to have to refine it and spend a lot of energy refining it. And then after that, we're going to have to pipe it somewhere, take it by a truck, and take it to where people can use it. That sounds like a lot, right? Well, that's what we're doing right now with oil, and similar to coal. We're spending a ton of resources, a ton of money. That's why gas prices are going up, because it's getting more expensive to do these things. So we know we're going to run out of gas at some point. Why not go ahead while we've got this technology and transition to these renewable energy sources? And if we have these are everywhere. We don't have to be dependent on Saudi Arabia anymore. We'll have everything we need right here. So that's just a little bit different view I wanted to share with you on this topic, because it really is important to have context when you're thinking about these type of things. Here we have just an example of a wind farm. This looks like a typical wind farm you would see in the American Midwest. And here is a cross-section of a wind turbine and generator. Even today, I'm seeing on the news all the time, they're refining designs on turbines. They're making them bladeless now even. They spin in a circle like a vertical cylinder rather than have big blades. They're more efficient, less intrusive to the environment, less wind is needed to turn them. The technology is improving all the time. Wind generating capacity. This is just a chart that shows how Europe, that pretty much produces a similar amount of electricity or power that we need and use here. United States, we're in red. You can see that Europe has greatly surpassed us in the renewable energy production. This is just wind, but they've surpassed us in every way pretty much. Now, geothermal, there's two. I look at geothermal kind of as two different types of geothermal. There's This is the what I call a true geothermal, where we're tapping the hot mantle or upper or lower crust of the earth. We've talked about plate tectonics and all that earlier in the semester. So there's fissures that come up that are pretty hot still, and if we can access those, if they're close enough to the surface that we can drill down and tap that heat, then we can use that big, I said the sun was a free nuclear reactor in the sky. We also have a free nuclear reactor in the center of the earth. Doesn't cost anything. All we have to do is get to it, to utilize it. So if we can drill down and access this hot material down here, then we can run turbines on the surface, superheat water, run turbines, generate electricity. And that is another alternative. Now, of course, this has to be somewhere, probably not Kentucky, because we're not very tectonically active here, but out west, they're much more tectonically active. There are many more hot spots near the surface. Look at a place like Iceland. They really use a lot of geothermal energy in Iceland. That's an island, relatively small population, but the whole thing is just a geothermal bubble in the middle of the ocean. It's volcanoes, earthquakes all the time. They really use this there. And this is a map of the United States with those kind of hot spots where it would be really practical to use geothermal. So again, here we go. There's another part of the country that we have covered with another renewable type of energy. So as you can see, as we go through these different ones, we're kind of covering a whole lot of the country. Not as useful over here in our area in the eastern United States, but still we have parts of the country that it does work. Now here on the right side is a picture of Iceland. Again, this is one of the cooling ponds of the water they're using in one of their plants. People go swimming in the winter there because the water's so warm. It's kind of like a artificial hot spring that you would find in the mountain somewhere. And this is just a map of Iceland and their use of that power. Now here in Kentucky, we also use geothermal power, but it's a different scale and really a different type. So you all know I'm quite familiar with caves and karst. And if any of you have ever been in a cave in the area, you know when you step in that cave, it's always 56 degrees. No matter what time of the year it is, it's 56 degrees in the ground. The reason for that is the surface, the ground below us, takes on the average temperature of this area all year round. So if you took all the temperatures from summer to winter and you averaged every second of every day, it's going to be around 56 degrees. So as you dig down and get down to depth where you're not being directly affected, probably 30, 40 feet below the ground, you're going to have temperatures of 56 degrees all the time. So while that's not extremely hot, it's not hot enough to provide power to boil water or keep your hot water heater hot. It is constant. So, for instance, in the wintertime when it's cold outside like it is right now when I'm making this video, when it's 30 degrees outside, that 56 degrees is going to feel better than 30. So while we're not going to be able to use that to heat our entire house because we want it to be, around 70, it could assist in moderating the temperature within the house so we don't have to use as much of the electric heat. Same in the wintertime. In summertime, in reverse. So when it's 95 degrees outside, 56 degrees feels pretty good inside, right? So we can use that temperature from the ground, pump that up, and use that in a geothermal system here in Kentucky to where we can moderate our temperature inside when it's really hot outside. That's how our geothermal work. It's not the extreme hot that you have in those hotspot areas, but it's a moderating factor in a place like Kentucky. We have ocean thermal energy. I'm not going to get into this too much, but anywhere you have a deep ocean alongside of a coastline, so in other words, you don't have a really wide continental shelf out here. If the ocean drops off pretty deep, pretty quick, you have access to both warm surface waters and cold water down deep. You can set up a system. I'm not going to go into the details of that, but it can be a floating power plant or even a ship out or away from the land. and you can produce energy like that. That would be very common along the coastlines of the world. Now, tidal power is something that I think is something that's going to get more and more popular as we go. We talked about hydroelectric power, and it's already used a whole lot in the world. Tidal power is the same concept of hydroelectric in one regard. If we have a bay, remember when we studied plate tectonics and the coastlines and how we have bays and inlets and all that, there's always a high tide and a low tide going in and out, so that produces a current. So if you can put structures in place to capture that water as it goes back through, it comes in and goes back out, as it coming in and going back out, if you have turbines in there, those will spin and you can produce electricity from that. So that's kind of a high tide, low tide kind of tidal power, very, very similar to hydroelectric power. And then you have places that have ocean currents that are much deeper sometimes, but are very, very strong. And you look at this picture as an example. Now, me as a whitewater paddler, when you see a structure or anything in the water and you see water flowing past it with this much turbulence behind it, that water's really moving. That's a strong current for the ocean. So down under this, you have these big turbines, just like wind turbines, that will spin in this current. And that can create electricity by spinning these turbines, as we talked about over and over and over again. So this is pretty close. This is actually a bay where you have a lot of current coming through here. They're looking more and more into putting these out in the deep ocean currents. Like off the coast of Japan, I've seen recently, they have actually constructed something not like this. It looks like a big tunnel, but they have turbines inside of it that spin, and they sit it on the bottom of the ocean. And that current is so strong, it spins those turbines, and that electricity is pumped through cables up to the mainland. Now, here's a little bit different type. I pulled these pictures off the internet. These are wave power. So we've all been on the ocean, and you how the ocean waves up and down, constantly just waves. So these are individual arms, and all they do is float on top of the ocean. And as the waves go up and down, it's turning a turbine inside the structure. And it continuously goes with the waves, and that motion is producing electricity. And as you can see here, these are just pulled up in case there's like a storm or something. They could pull these up and keep them safeguarded until the storm passes. So again, more renewable energy here. And then we have the example of a hydrogen engine. This is a combustion engine, very clean, very efficient. It only uses hydrogen, and it pulls oxygen from the air around us. So it pulls in the other part of the fuel from the air, and it splits those atoms, and you get a product of energy and water, H2O. Very simple process. In my opinion, from what I've seen, I think this would be a superior alternative to battery-powered cars charging on electricity. However, we're going to more and more battery power. And the reason we're doing that is essentially because it's a low-hanging fruit, because we already have electricity everywhere. So we can set up a charging station in our home, any store. There's already electricity there. We've been using electricity for years for everything else. So it's easy to set that system up. If we went straight to hydrogen from gasoline, we're going to have to set up hydrogen tanks and fueling stations everywhere like we have gas stations. That would be a tremendous expense on the front end, and that's something people just don't want to do right now, is have that expense. Although I think long term, hydrogen is a much better technology than using battery power. I'm all for battery powered cars over fossil fuel gasoline cars. I am for that. I just hope that we have a plan in place for the batteries to be recycled and reused on the back end of this. I hope they have this figured out already. And you would think they would. I know the scientists probably do, but have the car manufacturers bought into that? That's going to be the big question. Because again, I'm going back to what I said before, and I don't want to sound too biased, but it's the real world. They're just concerned about money right now. They're doing what's going to make them the most money. So I hope they have this figured out. I hope they're looking ahead to this. This is just a chart that shows how we use energy within the home. And if you look, the vast majority of our energy expenses in the home are heating and cooling, just our air conditioning and our heating units, and water heating. So our hot water, showers, the dishwashing, all that stuff. The other stuff is less. It adds up, but it's generally less. And the image on the right is just a thermal image of a house, and this is not a very efficient house apparently because it looks like it's losing a whole lot of heat at nighttime here. I'll let you look at this in a textbook. This just talks about energy demand on a daily basis. That demand goes up and down. It also fluctuates depending on the time of the year. If we're in the middle of a polar vortex and the temperature is below 20 degrees for 3 days, it's going to be a much higher demand all day long. Same way if we have a extreme heat event in the summertime, we have 100-degree days for like a week in a row, you're going to have that heat demand kind of flatline on the upper end of that. And that's why you see states like Texas that will not invest in their renewables on their energy grid have these blackouts for days on end when that happens. That's pretty much it for this lesson. Again, if you need anything, let me know. I'm open to discuss or help anytime. Thanks.